Okay, in this video, we are going to do a very quick touch on some vector addition and then finding the resultant displacement of that vector addition. So it's going to be a really quick touch on it. Hopefully it's enough information. Let's see. So we've got a dodgeball player who is trying to avoid getting hit by the opposing team. The player runs 2.7 meters at an angle of 37 degrees, then runs 4.9 meters at an angle of 62 degrees. Then he runs 1.7 meters at an angle of 13 degrees. Rounding to 2 decimal places, find the magnitude and the direction in degrees of the resultant displacement when the 3 vectors are added together. So a couple of things here. I have already drawn those vectors out here with their respective angles. So the orange one is our 4.9 meter at 62 degrees. The green one is our 2.7 meter at 37 degrees, and the blue one is our 1.7 at 13 degrees. Now, what vector addition does is it will take each of these and it stacks them on top of each other. And the resultant vector is going to be kind of what they equal in the end. And so I can just move this vector and put its tail on the end of this one, on the head of that one. And then I can move this vector. And I can do the same thing. So our resultant vector, if I take out this ruler, is going to be from here to there. So from this end to that tip. This is going to be our resultant vector. And there are two things that we want to find with that. So we want to know what is this angle, and then we want to know what is this length. And we're going to use vectors to do that. And so what we're going to have to do is figure out all these different components. So with this blue piece here, we could figure out the vertical component, and we call the vertical component J. And we could figure out this horizontal component, and we call that I. And we know that its length, is 1.7, and we know that its angle is 13 degrees. So when we have these all added together, what we really need to do is we need to find all of the horizontal components and all of the vertical components. So all of our horizontal components are here, and then it's going to be here, and then it's going to be here. Those are all our horizontal components. And to find horizontal components, it is very similar to our polar coordinates. And in our polar coordinates, x equaled r cosine of theta. Now here, we are saying, because we're talking about vectors, x is I. So I means horizontal component. R of this line here, because we're going to have 3 of these. There's going to be the blue, the green, and the orange horizontal component. So the blue's horizontal component is going to be 1.7 times cosine. I guess I should do that in blue, so that you can see where this is coming from. So the blue's horizontal component is going to be 1.7 times cosine of 13 degrees, because this is 1.7 and then the angle is 13 degrees. The green's horizontal component is going to be 2.7 times cosine of 37 degrees. And then the orange's horizontal component is going to be 4.9 times cosine of 62 degrees. When we add all of these together, we get the total horizontal component. Okay. So our total horizontal component is going to be 1.7 times cosine of 13. I want to make sure that this is in degree mode. I did change it to degree. Plus 2.7 times cosine of 37 plus 4.9 times cosine of 62. So our total horizontal component for our new galaxy line, I, is going to be 6.019. Okay, now we want to figure out the vertical component. And if we think back to this, vertical is y. So we're going to now use our sine of theta. So let's look at the blue piece first. Remember, this distance was 1.7 and this angle was 13. And so the j component of the blue is going to be 1.7 times sine, I don't know why I almost wrote cosine, times sine of 13 degrees. The j component of the green, so that's going to be right here, is going to be, remember, this was 2.7 and this angle was 37 degrees. So the j component is going to be 2.7 times sine of 37 degrees. And then lastly, the orange component of this, the orange vertical component, remember this is 4.9 and this is 62 degrees, is going to be 4.9 times sine of 62 degrees. And to get this entire line, we need to add the orange, the green, and the blue. So we will add these together. And that's going to give us our entire j component. And so let's go ahead and take our calculator again. And we're going to do 1.7 sine of 13 plus 2.7 sine of 37 plus 4.9 times sine of 62. And we get that our j component of this is going to be 6.334. Now, does that make sense? When we look at this, those look like they're almost even. Those look like those are almost even. And if these are almost even, this angle that we're solving for, this theta, should be close to 45. Not exactly, but close. So now we need to find our magnitude. And this goes back to a previous video. So if we know that this is 6.334 and that this is 6.019, well, r squared would be I squared plus j squared. And then to get r, you would do the square root of that. So r, or the magnitude here, is going to be the square root of 6.019 squared plus 6.334 squared. Let's plug that into our calculator. So we have the square root, oops, let's put that in a different tab. The square root of 6.019 squared plus 6.334 squared, and we get 8.74. So R is 8.7, I already forgot, 8.738. 8.738. That is the distance. So our resultant vector is we need the magnitude and the direction. So our magnitude is 8.738. That's the magnitude. Now, how do we figure out direction? Well, it says in degrees, so that's a really good hint. The direction is going to be the angle. And there's a really easy way to figure this angle out. We have opposite and we have adjacent. So we're going to do tangent of theta equals 6.334 divided by 6.019. And then we're going to inverse tangent that. And that's going to give us our angle. And so let's go back to our calculator. And we are going to do the inverse tangent of 6.334 divided by 6.019. And our angle is 46.5 degrees. And that makes sense because they're pretty close. So 46.5 degrees. Okay, so our final answer for this question is the resultant vector has a magnitude of 8.738 with a direction of 46.5 degrees.